Okay, um, greetings everyone. So this is our lecture on Chapter 9, the binomial distribution, which we have started. So the real issue for us today, for you at home, is we're not going to use the statistical tables anymore because we can use Excel. So the purpose of this lecture is to show you how to compute binomial probabilities in Excel, and then also to show you a little preview of computing probabilities in the normal distribution in Excel. So just for those who weren't there last week, the binomial distribution is a probability distribution that can be used to analyze probabilities whenever we have a series of trials, N trials, or experiments, or whatever we want to call them. And each trial or observation we make can take only one of two possible outcomes. The outcomes are mutually exclusive, which means that one and only one outcome can happen on each trial, excludes the other one. And then each trial is independent. And then the probability of either outcome stays the same from trial to trial. So the best example of a binomial set of binomial trials is a series of coin flips, right? So for example, if we flip a coin 10 times in a row, we have a series of 10, n equals 10 trials. Each trial, we only have two possible outcomes, heads or tails. Those outcomes are mutually exclusive. Each trial, each flip is independent of the previous. You remember, statistical independence means that the probability of a coin landing heads on the second flip is independent of the probability that it landed heads, or the fact that it landed heads on the first flip, and that's true all the way out. And each flip, right, the probability of heads stays the same, it's 0.5. So I'm going to skip over this, and the book talks about some various terms that we can use. So the reason the binomial distribution is called the binomial, part of it has to do with the actual computation of probabilities comes from the binomial expansion. So it is important to recognize that in any binomial problem, we have two probabilities, probability P, which is the probability of one of the outcomes of interest, Q, which is the probability of the other outcome, and Q is always equal to 1 minus P, because something has to happen on any trial, coin flip, for example, heads or tails has to result. So there's a 1.0 certain chance that something will happen. So that 1.0 is split up between P and Q. Sometimes it's 50-50, 60-40, so on and so forth, but it has to add to 1. And then N is going to be our number of trials or flips or so on. So in the book, we derive this, and I show you the binomial table. We don't have to use that anymore, which is kind of nice, right? Let's skip ahead to actually doing this with Excel, right? So the Excel function that we're going to use is called binom dist range, and we're going to type it out like this. It takes 3 to 4 arguments. Remember, an argument is just information we give to the function. So you'll see what I mean in a minute. We can use this function to do two things. We can get the probability of a single event. So for example, the result that when we flip a coin 6 times, we get 6 heads. We can get just that, or we could get a range of events. We could get the total probability across the range, which is an OR, which is the addition rule. And so this function in Excel allows us to do both. It allows us to get single probabilities, and it will automatically perform the addition rule for you. So this is just some information about how Excel interprets what it calls the arguments. So I'm going to use the letter N. That's the first argument to the function, which is the number of trials that we're going to perform. The small letter P for the probability of success on any trial, and X for the actual number of successes that we want the probability of. So if we look at the next page, we've got two examples. So here I show you a screenshot of Excel, but let's actually do this. So we'll start with coin flips, and P for a coin flip, the probability that a coin lands heads is 0.5, right? Half chance. If we want to know the probability of 6 out of 6 heads occurring in a series of flips, we're going to use the binomial dist range function with 3 arguments. So it will look like this. Right? So you'll type equals binomial dist range. And the first argument, you can see it says trials, right? So we're going to flip a coin 6 times, so 6 trials. The second argument is probability sub S, which is probability of success. So a success for us is heads. We decide what success is. It's heads. So we say 0.5. And then we can give it 2 additional numbers or just 1. So for this one, we're only going to type in 1 number because we're only interested in the actual event that 6 of the 6 tosses are heads. So we just type the number 6. Right? And we press enter, and we get that probability is 0.1562525, right? And you can see that right here. And in fact, if we go back to the book, right, that's actually what we would have found using the book, right? So so this is just giving us what the book would have given us in a much easier format. Okay? So when you do this, when you want a single type of event, so just one result that you're interested in calculating the probability of, you use 3 numbers. Often, though, we're going to be interested in something like this. What's the probability of at least 4 heads in 6 flips, right? So that's the probability of 4 out of 6, or 5 out of 6, or 6 out of 6, right? That's an or. So before, what we would have had to do is look up each of the probabilities. Now we don't have to do that, right? Simply all we need to do is, the syntax is over here, so we'll type it in, right? So this is P of 6 out of 6. If we want P of at least 4, which is 4 or 5 or 6 heads, we simply add a 4th number to our function, right? So we're going to type binomial dist range, and we're still flipping the coin 6 times. The probability of a head is still 0.5, okay? So now what we're going to do is we're going to type in the lowest number of heads that we're interested in, and that's 4. And then we're going to type a comma, and we're going to say, what's the highest number of heads? Well, the maximum number of heads we could get out of 6 flips is 6. So when we ask for at least 4, what's probably at least 4 heads out of 6? We type in the 4, and then we type in the 6 because that's the last event. And this gives us 0.34375, which you see here. And simply to show you why, let's do the following. Let's do number of heads. So 4 heads out of 6, 5 heads out of 6, 6 heads out of 6. I'm going to use this version of the function to compute each of these single probabilities, and you'll see that they add to what the function gives us, right? So if I wanted to know the probability of out of 6 coin flips with a P of 0.5 on each flip of 4 heads, right? That's 0.234347, or 375, excuse me. If I want to know 5 out of 6, I type in my 6 trials, 0.5, and 5, right? And I see that the probability is lower, right? So it's less probable to get 5 out of 6 heads than it is 4. And if I do the last one, I'll get the same as above, right? This is binomial dist range, 6.5 and 6. I get what I had before. Now, total probability of 4 or 5 or 6, right, is the sum of those 3, which is identical to what this function gives you. All right. So this binom dist range is super handy. So that's what you're going to use for this chapter and the next chapter. Anytime you have a binomial distribution, you're now going to have Excel all the time. You can use this. Okay. All right. So the reason that we're interested in the binomial distribution is actually because it can help us interpret experimental data. So we went through this example in class, but I want to do it again, okay? Because this is actually the type of example that we're going to learn how to interpret in the next chapter, in chapter 10. So to summarize, right, let's imagine we have an experiment in which we want to see if our friend truly is a coffee connoisseur, meaning that he claims that he can taste the difference between Starbucks and every other type of coffee, right? So what do? One way we can test this is we can blindfold him, right, and give him 6 taste tests, right? Now, if we do that, and all of this other stuff is basically to say we randomize everything to make sure that the probability that he gets it right on each trial out of 6 is equal. That's important for a binomial problem, right? So in this experiment, right, let's assume this logic. Let's assume that to test whether our friend really knows what he's talking about, we actually make a skeptical assumption. We assume that he can't tell the difference between Starbucks and anything else, right? We assume that he's probably guessing. Now, this is just an assumption for our test. Right? So under this assumption, which we might call a null hypothesis, the best P probability of success for our friend on each trial is a coin flip if he's guessing, right? He's got a 50-50 shot. He can either guess the correct Starbucks cup or he can't. Okay? Now, if that probability, if we have our friend solve the problem or do the experiment, let's say that he actually gets all 6 out of 6 correct, right? If he does that, and that probability of that result happening, if he's truly guessing, if that probability is low, then maybe our logic is flawed. Maybe we could reject the assumption that we're making, right? So this logic will develop in the next chapter, right? But how do we set this up as a binomial problem? Well, what's n? Well, if we give him 6 taste tests, that's 6 trials, n is 6, right? What is p? Well, we'll develop this in the next chapter. If we're doing any type of binomial test in which we would want to be skeptical, we set p at 0.5. So we're going to set p at 0.5 for this problem, just like a coin flip. So it's an identical problem to the coin flip. Now, your book calls the event of interest a p event, right? So that's him getting it correct, right? So if he gets 6 out of 6 correct, there's 6 p events, and we're going to call that x from now on, right? So now this is equivalent to our coin flip problem. If he gets 6 out of 6 correct, in which if he's guessing, his probability that he guesses correctly is 1/2 or 0.5, we've already computed this probability, right? We've done it right here, 6 out of 6 successes with a probability of success on each trial of 0.50, right? So we find that if he's truly guessing, the probability that he would get 6 out of 6 right is 0.015625, which means that if we were to do this experiment with him 100 times over, so give him 6 taste tests, right, and figure out how many he got right, we did that over and over and over again in a world in which he's really guessing, right, the probability that he would get 6 out of 6 should only happen once out of every 100 trials if he's guessing, right? So again, I've showed you how to enter that, right? And since this is a relatively low number, maybe our hypothesis that he was guessing is incorrect, right? So this is how we're going to use probability going forward, and we're going to learn a lot about this after this chapter is over. So I just want you guys to sort of start to get your head around that. But before we do that, we're going to just practice computing binomial distribution probabilities. And then in a minute, we're going to learn how to use Excel to calculate probabilities on the normal distribution. And then we'll use that later on in the course in chapters 12 and in 13 and 14. Okay? All right. So I'd like you now to stop the video, pause it, and try to solve these two problems in Excel. All right? So the first problem is a key shop advertises that the keys made there have a 0.9 probability of working effectively. Right? If you bought 10 keys from the shop, what's the probability that all the keys would work effectively? The second problem is a student is taking a true-false exam with 15 questions. If she guesses on each question, right, what's the probability she'll get at least 13 questions correct? Okay, so see if you can do this in Excel on your own, and then so pause the video and try it, and then come back and we'll look at the answers. Okay, so hopefully you paused and tried this. If not, you can go back and try it again. So for the first problem, right, we're always interested in, well, what's n, the number of trials, right? So this is the number of keys, right, that you make, right, at the key store. Each key has a probability of working of 90%, 0.9, right? There's only a 10% chance that the key, you get it home, it doesn't work in your lock, right? So we're interested in then, given that, what's the probability of buying 10 keys or making 10 copies and all 10 of them working, right? So we see over here that we would type in, and I'll do it for you, right? We'd type in equals binom dist range. Our number of trials is 10. Now our probability of success is 0.9, and we're interested in 10 out of 10. Right? So it's actually not a very large chance, 0.34, 8, 6, 7, so on and so forth. So why is that? Well, because each key is not guaranteed to work, right? It's got a high probability of working, but that means that actually if we did this, the highest probability, if 90% of the keys work and you bought a bunch of keys, the highest probability is that one of those 10 keys wouldn't work. But again, the point here is to understand that in the problem, you want to be able to deduce these three numbers, right? The number of trials that are being performed, right, which is really a number of opportunities for observation, the probability of success or some event of interest on each trial. In this case, our event of interest was that a key would work, right? So P is always the probability of the event of interest happening in one trial, and then we're given an example, we're given a piece of information that we've got to solve for a number of trials, right? So across 10 trials, what's the probability, right? Across n equals 10 trials, what's the probability of x equals 10 successes or working keys with a probability of a single key that's made working of 0.9, and we found it. Right? The second one, right? We've got someone taking a 15 item test, true false test, right? So if we think of each item on the test as a trial, there's 15 items, n is 15. It said in the problem that they're guessing. What's the probability that if they're guessing on each one, right, that they get at least 13 right? Well, the probability of getting multiple choice question correct if you're guessing should be 0.5, right? So we use that to represent guessing. I asked for the probability of at least 13 successes, which means the probability of 13 or 14 or 15, right? And so this is the nice thing that we can do with our range, oops, that's actually a spelling error. Let me just change that. We can do with our range function is we don't have to go ahead and get those probabilities separately, right? So again, the way I do this is I say, okay, binom dist range, 15 trials, 15 multiple choice questions, 0.5 probability of getting it right if you're guessing. And we want at least 13. So 13 is the lowest number of successes of interest. And then the maximum we could get is 50. So at least 13 means 13, 14, or 15. So we've got to always type that last number correctly. And if it's an at least problem, that last number is gonna match n. The highest that you can do is n successes, 15 successes out of here, right? And we get that that's a very small chance, right? So 0.00369 and change, right? So about 3 times out of 1,000 test takers so about 3 out of 1,000 test takers, if they're really guessing, would get 13 correct on a multiple choice exam, 13 or more, 13, 14, or 15. All right. So these problems are actually in your book, so you can try them again, and just make sure you know how to use this function, okay? All right, so the final thing that we want to talk about is the fact that we can also use Excel to get normal distribution probabilities. Now, the normal distribution is trickier because it's a continuous probability distribution. We learned it in terms of percentiles, and that's the way that we're going to use it. We're actually going to use it in 2 ways now. We're going to use it in percentiles, right? Which in our binomial problems is equivalent to actually asking, well, what's the probability of at most this number of things? And then we're also going to use it in terms of the at least question. So let me demonstrate this first, and then we're going to, then you can try it. And again, all of this is, you're going to try all of this on your quiz. Okay, so the function in Excel is the norm dist function. Right? The default for this function is to give you the percentile, right? For any variable for which you have either a z-score or the actual, we don't even have to make it into a z-score. You can just supply the parameters of the distribution, and I'll show you what that means in a minute. If you're asked, what's the probability of scoring below a particular x value on a normally distributed variable, you're going to use norm dist directly. However, we're going to want to be able to also answer a question, well, what's the probability of scoring above a particular point on a normal distribution? And to do that, you're actually going to have to type something like this, 1 minus norm dist. So let me just show you this, and then I'll explain it, okay? So let's start with an example of the Beck depression inventory. The way norm dist works is you have to know, as we did before, you have to know what mu is, you have to know what sigma is, right? You have to know the mean of whatever this normally distributed variable is, and you have to know sigma. So let's say that in the population of people, non-depressed people, the Beck depression inventory average score should be 15 with a standard deviation of 4. So we're going to do 2 things right now, and this is all we're going to be concerned with normal distributions. Let's first find the probability that if I randomly select someone from the population, all right, and I give them the Beck depression inventory, what's the probability that they'll score below 17, right? So this is akin to getting the percentile for a score of 17. Right? So you see it over here, but let me explain what this function is all about. Right? So to zoom in a little bit more, Excel gives you clever pieces of information about what you're trying to do, right? So the norm dist function, when I press open paren, it asks me for 3 things. The first thing it asks me for is x. Well, in this problem, x is the person's score. It's 17, right? The second thing it asks me for is the population mean, or mu. Well, for back depression inventory, for this example, we're just saying it's 15. So we type in 15. The next thing it asks for is standard deviation. We know that to be 4, that's sigma. The last thing it asks you for is, it says cumulative. We're only going to use the cumulative type of this function, but you have to type the following thing. You have to type true, okay? So it gives you the cumulative distribution function, which is a clever way of saying it gives you percentile information, right? So if I type in those 4 things, x, mu, sigma, and true to give me the cumulative, right? I get the probability, which you see over here, okay? 0.6914 and change. That's the, or 69% chance, or the percentile of a 17 on back depression inventory is 69.15. Right? Your person's in the 69th percentile. So anytime you have now a normal distribution question, you don't have to transform to z-scores necessarily. Right? If you know mu and sigma, which we do here, right? You simply now just type those in along with x, the norm function. And again, you always type true at the end of that function. Let's try the probability that a random person scores, oh, this should just say above 17, right? So at least 17. How do we do this? Well, whenever we want an above, all we have to do is use the following terminology. Okay? I'm going to delete this and imagine that we haven't computed this probability before. Okay, so if I want an above and I want to use norm dist, the first thing I do is type 1 minus, right? Because norm dist gives us the bottom of the normal distribution. If we want, so below 17, for example, if we want 17 and above, we take the full curve, 1.0, right? So we type that in there, and we subtract from it the bottom, below 17. So we're going to type in norm dist, right? X is 17, mu is 15, sigma is 4, and again, always type true. And we find that the probability of scoring above a 17 is 0.3085, right? Which we see here, which is literally equal to 1 minus what we just found there, okay? So at this point, you can try the quiz. You get 3 cracks at it. So go ahead and try the quiz. There will be some binomial problems. There will be a couple of normal distribution problems. Use Excel. That's the point of this exercise, is to now use Excel on your quizzes and on your exams. And in the meantime, email me if you need some help. And this coming Thursday, the 26th, I believe, is our first Zoom in-person session for question and answer. And we'll go over all of this stuff that doesn't make any sense. Okay? Thanks a lot, and I'll see you in person very soon.